Up to now, we have dealt with point charges, the simplest idealization. But nature rarely arranges charges at single points. Instead, charges spread over lines, surfaces, and volumes. Today, we will derive electric field and potential from first principles, and you will notice an elegant pattern. Break the distribution, pick a tiny delta Q, integrate. Instead of discrete charges, charge is assumed to be smoothly spread. 3 types. 1. Linear charge density is equal to 2. Surface charge density is equal to 3. Volume charge density is equal to. These densities may be uniform or varying. In G, both appear. Uniform is simple, non-uniform is beautiful. For any distribution, choose a small element with charge dq. Write distance r from dq to point of observation. Write field due to dq is equal to 1 asterisk superscript to asterisk. Use symmetry to simplify components. Integrate. This method is the backbone of all electrostatics derivations. Consider a long rod, charge density lambda, take small element is equal to. Field at point P is equal to 1 asterisk superscript 2. Use geometry to express r in terms of x, integrate over length. For an infinite line, the result elegantly becomes is equal to. Take an arc of radius r, uniform lambda is equal to. Field contribution, horizontal components cancel, vertical components add. Thus, is equal to 2 asterisk sin. For a semicircle, is equal to 2. This is asked many times in G Advanced. Ring radius r, total charge q. The beauty is, all radial components cancel. Only the axial components add. Take dq is equal to lambda d theta is equal to. Vertical component is equal to cos is equal to asterisk. Integrate is equal to. A professor's insight. Rings are the parent case. Disks, cylinders, and spheres emerge from integrating rings. Disk of charge. Take ring of radius r and thickness dr is equal to. Field contribution is equal to. Integrate from r is equal to 0 to r is equal to 2. At large distances, superscript 2. At x is equal to 0 is equal to 2. Infinite plane sheet, a gem of symmetry. Taking disk let r is equal to. This field is constant, independent of distance. A very important conceptual result. Electric field of a uniformly charged sphere. 2 cases. A. Outside sphere field behaves like point charge is equal to 1 asterisk superscript 2. B. Inside sphere use volume density. Enc is equal to asterisk superscript 3. Thus, is equal to. Field increases linearly inside a uniformly charged sphere. A beautiful and important result. Non-uniform densities. Examples: 1 lambda is equal to kx. Charge increases with x. Integration needed is equal to. 2 sigma is equal to kr. Surface charge depends on radius. Integrate carefully using polar coordinates. 3 rho is equal to kr superscript 2. Volume charge density increases with distance. Results in cubic expressions in Gauss method. Senior advice: do not fear non-uniformity. It simply means integrate patiently. G PYQs, tricky styles. The following types appear every year. PYQ1, field of finite rod on axis. Students often forget to break into components, wrong answer. PYQ2, arc of charge. Mostly asks direction and magnitude at center or axis. PYQ3, field of ring or disk. Common trap, forgetting the in denominator. PYQ4, non-uniform lambda, lambda x or lambda 1/x demands clean integrals, not tricks. PYQ5, sphere. Students often incorrectly assume inverse square inside. But inside, field is linear. Master insight. All results in electrostatics are simply different integrals of Coulomb's law. If you understand symmetry and geometry, you can derive any field expression in 30 seconds.